You ever drive by one of those huge highway cuts through a hill and just wonder, how is that giant wall of dirt not just collapsing? Well, today we're going to dig into the invisible engineering that makes all that possible. We're exploring the really amazing science of soil reinforcement.
It's a weird question when you think about it, right? I mean, we can stack steel and concrete 100 stories high in the middle of a busy city, no problem. But then sometimes, building just a simple house on what looks like perfectly solid ground is a huge engineering nightmare. So what gives? The answer isn't in the building itself, it's what's underneath it.
And that's the heart of the problem, right there. The ground itself can fail. See, soil has its limits. It's actually great if you squeeze it, compress it. But the second you try to pull it or stretch it, it's terrible. And under the wrong kind of stress, it'll just give up. It'll shear, slide, and fail, taking whatever you built on top of it right along for the ride.
Okay, so if the ground itself is the weak link, what's the fix? Well, this is where engineers got really clever. They came up with this brilliantly simple idea. If the soil is weak, let's just make it strong. Let's give it a skeleton. This brings us to the key concept, reinforced earth. And the best way to think about it is, it's just like reinforced concrete, Concrete is super strong when you squeeze it, that's compression, but it'll crack if you try to bend or pull it. So we add steel bars, rebar, which are amazing at handling that pulling force, what we call tension. Reinforced earth uses the exact same logic, but for dirt. We're combining the soil's natural strength with materials that can handle all that tension. And this visual shows you the magic right here. It's a crucial transformation. On the left, you've got normal soil. It's brittle, which in engineering is a bad word. It means it can fail suddenly, catastrophically, kind of like glass shattering. But on the right, with reinforcement, we've created a whole new material. Its behavior changes from brittle to ductile. So instead of just snapping, it bends, it deforms, it gives you a warning. And that makes it far, far more reliable and a whole lot safer.
Okay, so how do we actually do this? Well, the first major method is what we call reinforcing with inclusions. And that's really just a fancy way of saying we're going to mix materials into the soil to strengthen it from the inside out.
One of the most common ways is with strip reinforcement. These are basically long, flat ribbons of high-strength material. We're talking galvanized steel or some pretty advanced polymers. As a retaining wall gets built, these strips are layered within the soil, acting like internal tendons that hold the entire mass of earth together. Another really powerful tool is grid reinforcement, usually called a geogrid. This is a mesh-like sheet made from tough polymers. And the genius of the geogrid is that it literally interlocks with all the soil particles, creating this super stable, unified mat. This stuff is an absolute game changer. It lets us build incredibly steep slopes, put roads over swampy, mushy ground, and by doing that, it unlocks huge economic value by turning previously useless land into stable, buildable real estate. But what if you're not building something new from scratch? What if you need to stabilize a slope that's already there? You can't exactly go back and mix things into it. And that's where our second big method comes in, pinning the ground down from the outside. This technique is called soil nailing, and the name is pretty literal. The idea is to drill and install a whole series of long steel bars, the nails, right into the ground. You're basically stitching an unstable soil mass to the stable solid ground that's behind it. It's like putting thousands of pins into a giant cushion to hold it right in place. And there are a few different ways to do it. The most common is probably the drilled and grouted method. You drill a hole, insert the nail, and fill the gap with grout. For something quick and temporary, you might use driven nails, which are just hammered in. Super fast, but they can rust. Then you get the more advanced stuff, like self-drilling, where a hollow bar drills the hole and injects the grout at the exact same time. And for really fast work, nails can even be launched into the soil with compressed air. Each method is just a different tool for a specific job.
Now, soil nails are great for holding a slope together, but sometimes you need to resist just immense pulling forces. Think of a massive dam holding back a lake, or a tall skyscraper resisting the wind. For these foundations in tension, where a structure is literally trying to lift itself off the ground, engineers need an even more powerful tool, ground anchors.
So how does a ground anchor work? It's kind of like a giant toggle bolt for the planet. First, you've got the anchor head, which is the part that connects to the structure, like the dam. That's attached to a super high-strength steel cable called a tendon, which runs deep, deep into the earth. And at the very end of that tendon is the fixed anchor, which is where it's grouted into solid rock or stable soil.
So the whole point is, any pulling force on the structure gets transferred safely way deep into the ground, where it can't cause any problems.
Okay, so these are all fascinating engineering tricks. But so what? Why does mastering the science actually matter so much? Because these techniques are quietly at work all around us every single day, making our daily lives safer.
Seriously, this technology is everywhere. It's holding back the walls of deep city excavations. It's saving old, failing retaining walls from collapse. It's anchoring massive dams against the crushing force of water. Its role in public safety is absolutely huge, stabilizing active landslides, preventing rock falls on highways. From pipelines to tunnels, this is critical, life-saving work.
So the next time you drive past a steep, engineered slope or you see a massive retaining wall, you'll know what's really going on. That's not just a pile of dirt. It's a highly engineered composite material, one that's been given a skeleton of steel and polymer to make it strong, stable, and safe. It's the invisible engineering that literally holds our world together.
And that just leaves us with a final thought. We've uncovered one type of this hidden engineering that makes modern life possible. So what else is out there, quietly working in the background, that we rely on every single day without even noticing?